Okay, good morning. Today, what I'd like to do is to continue talking about reactions in aqueous solutions. So in the previous meeting, I discussed the idea of solubility in water, solubility of different compounds in water. So one type of compound we talked about were alcohols. So we said that alcohols could dissolve in water. And there's also what we call sugars. So those are compounds that can dissolve into water. The second group were the salts. And so what we're going to do today is we're going to talk about different types of salts that do dissolve into water and salts that don't dissolve into water. So, good morning. So for example, sodium chloride, NaCl, it dissolves into water. So we would say it's soluble in water. Okay. Whereas calcium carbonate doesn't dissolve in water. So we say it's insoluble in water. Okay. And our focus today is going to be on this second group of compounds, the ionic compounds, some of which are soluble in water and some of which are insoluble in water. So insoluble means not soluble, okay? And if something is insoluble in water, typically it's a solid, not always. You know, oils, for example, are liquids that sometimes don't dissolve into water. Aqueous generally means dissolves into water, okay? So let's take a look at an example problem. And the example problem we're going to look at is drawing what are called net ionic equations. And the net ionic equation is a way of representing a chemical reaction that involves a compound that is insoluble in water. So we're focusing on this idea. You know, yesterday or day before yesterday, we talked about soluble, things that were soluble. Today, we're going to talk about things that are not soluble in water. So let's take a look at this one. Oops. So it says here we're going to be writing net ionic equations. And just so that you can keep up with where this is in the textbook, this is section 4.2, the second section of chapter 4. So it says here the following chemical reaction takes place in aqueous solution, and they write you a chemical equation, right? So AgNO3, aqueous, so that means it's soluble in water, it dissolves, plus KCl, aqueous, that means it dissolves into water, forms AgClS, that means it's insoluble in water, plus KNO3 aqueous, that means it's soluble in water. So nowhere in here is water really represented, right? Water is the main component of these reactions. So imagine inside of, you know, something like Kool-Aid. You've got all these things in Kool-Aid. You've got sugars, you've got dyes, you've got citric acid, you've got flavors, all those things are in there, but it's primarily water. Water is the main ingredient of these situations here. So AgNO3 is put into water. KCl is put into water. So you're just sprinkling them into the water and a reaction takes place. And the reaction is represented here. You can tell that there was a reaction because you have a new substance here, AgCl. AgCl was nowhere here, but now we have this new substance, AgCl. There was no KNO3 at the beginning, but now there is a new substance called KNO3. So we have a reaction here. One of them is a solid, and that's what we're going to focus on, this idea that some compounds are insoluble in water. Now, it's very difficult to actually come up with a good theory to describe why some compounds, some ionic compounds are soluble in water and others are not. So for example, KCl is soluble in water. NaCl is soluble in water. LiCl is soluble in water. All these compounds are soluble in water, but for some reason, AgCl is not. It actually looks pretty similar to KCl. It's a metal plus a chloride, but it's not soluble in water. Now, there are ways to, come up with some theories to explain why that's the case, but it's beyond the scope of this course. For the most part, all we're going to do is we're going to look at the ones that are, look at the ones that are not, and then analyze what happened, okay? Essentially after the fact, but we'll go on to a little bit more advanced than that. So this one's not. So if you see the S, that means it's insoluble in water, okay? Another example would be that, for example, Na2SO4 is soluble in water. Another example would be that K3PO4 is soluble in water. But calcium PO4 is not. And lead is not. So again, it's difficult to come up with a simple idea of why some are soluble and some are not. For the most part, we just sort of look at lists and see which ones are and which ones are not. And that's part of what we'll do here. Okay. So let's come back to the problem. It's a very specific question. It's asking us to write the net ionic equation for this reaction. And so the net ionic equation is AgNO3 and KCl. And that's going to form AgCl and KNO3. So I'm just writing this down directly from the question. And it wants us to write the net ionic equation. Okay. So here's an approach. When you go through internet and textbooks and all of that, you'll find there's different approaches to doing these. One of the major keys of being able to do these problems is you have to be able to write the formulas for ions. So if you have forgotten how to do that or never learned how to do it, now's the time to learn how to do it. The way we write formulas for ions is we recognize that ionic compounds generally have two parts. They're what are called binary ionic compounds. So when something is aqueous, you break it up into separate ions. Okay. You have to know what the charges are. Okay. If they're ions, they're going to be aqueous. Okay. So when you see this aqueous, that means that's telling you break this up into two parts. Two separate parts. So see this plus here? That means this is one thing and this is a separate thing, as if you were like taking apart something. You took it apart, so now they're separate. Okay. Same thing here, it's aqueous. So you break it up into separate parts. And we're going to put aqueous because ions are generally very soluble in water. Okay, now notice that takes up a lot of room. So I'm not even going to have space over on the right side to write this. I'm just going to write it underneath after the arrow. Okay. So now we see on the product side something which is solid. This is telling us it doesn't dissolve in water. If it doesn't dissolve into water, we don't write it as separate ions. We write it as a compound. And then this one is aqueous, so we write it as separate ions. Okay. So notice there's charges in here. When we write these equations, we have to write the charges. Sometimes people circle the charge, generally not though, but I will just to kind of highlight that I'm writing in the charges here. Okay, of course, some of these, nitrate is a polyatomic ion, potassium chloride and silver are monatomic ions. Okay, so this is what's called, it has a couple of different names. It's either called the ionic equation. So that's one name that people call it. Some textbooks will call it the complete ionic equation. And then still, some other people will call it the total ionic equation. So there is no accepted name for this, but it all says ionic equation in it. So whatever they want to call it, it says ionic equation. What this is telling us is that when this reaction occurs, both of the reactants dissolve completely into water. They ionize, they form ions in the water. They then precipitate. They form a new solid, which is right here. That solid, which is called silver chloride, will not be soluble in the water. And then finally, there's a second product, which is soluble in the water, which is called potassium nitrate. Okay, so that's called the ionic equation. But the question here is not what's the ionic equation, it's what the net ionic equation is. So here's what we do. The net ionic equation is concerned not with everything that's in the mixture. It's concerned with the solid. And the question is, what ions are used to form the solid? Well, here's the solid here, AgClS, or over here, I wrote it here. So we just asked which ions were used to make that? Well, it was the silver and the chloride. Those are the two ions that were used to form that solid. So what we do is we just pick those ions that made the solid. So we pick those ions, we write them as reactants, just like we did over here, and then we write the product on the product side. Okay, this is essentially a streamlined equation. What it's doing is it's ignoring the ions that don't make the solid. And the logic behind that is that when you added silver nitrate to the water, you get nitrate ions. After the reaction takes place, you still have nitrate ions. So there's really no reaction in the nitrate. The nitrate's not really reacting. The same is true for the potassium. The potassium was dissolved in the water, but it's still present in the form of potassium at the end. So that's not really any change. The net ionic equation is showing where the change is. And the change is a pretty simple one. It's that these two ions have combined to form a solid. And this is exactly the sort of thing that happens inside of bodies in terms of things like kidney stones. So we often will take in our diet something called oxalate. And oxalate will combine with calcium to give us calcium oxalate. That's insoluble in water. It precipitates out. And most people in their bladders have a certain amount of these little solids, which are called crystals. And if the crystals grow big enough, then they can block the ureter and cause, all kinds of pain and illness, right? Can eventually damage the kidney. So that's one example there. Shells, for example, animals that form shells to protect themselves, they generally use calcium and carbonate ions to form calcium carbonate, which is insoluble in water. That's another example of a precipitation reaction. So this section 4.2, what you're doing is you're essentially writing, hey, what are the ions that are making up this compound here? Okay. Let's take a look at another example. Okay. So again, writing the net ionic equation, the following chemical reaction takes place in aqueous solutions happening in water. So notice the form, very similar to the previous one, right? You've got two compounds that are soluble in water, to form one compound that is insoluble in water, and then one compound that is soluble, okay? So same idea, we're gonna write the net ionic equation. The way I'm gonna do that is I'm gonna write the complete ionic equation first, and then write the net ionic equation after it. Okay, so manganese sulfate. Sulfates are generally pretty soluble in water, SO4. Hydroxides sometimes are soluble, sometimes they're not. It just depends on what metal they're combined with. So if they're combined with potassium, for example, they're soluble, but if they're combined with manganese, they're not. Okay, so let's take a look here. Okay, let me just try to see if I can. Not gonna do that. Okay, MnSO4. So manganese sulfate, soluble in water, plus potassium hydroxide, soluble in water, manganese hydroxide, insoluble in water, and potassium sulfate, sorry, K2SO4, soluble in water. Okay. Let's take a look here. So first step is to break each compound that's aqueous. So you don't do it for the ones that are solid or for the one that's solid. You do it for the one, so I'm just going to draw one arrow because we're just going to bring that down. You do it for the ones that are soluble. Okay. And again, we're only dealing with binary ionic compounds. We're only dealing with ones that have two parts, a metal with a non-metal. So we don't have to worry about breaking it up into 3 or 4 parts. There are reactions where that happens, but we're not worrying about that here. Okay. So looking at your, the chart of polyatomic ions, you can figure out that the manganese is +2 and the sulfate is -2. Now, be careful here. You have 2 of the potassium hydroxides. So potassium and hydroxide are going to break up into 2 separate ions, but there's a 2 in front of it. So that means there's 2 of these, 2 of each of them. Then here's our arrow. Okay. So actually, I just want to be a little bit careful here because I didn't line it up perfectly. Let's do it this way. So there's your potassium, there's your hydroxide. So on the product side, this one's a solid, so it remains as a solid. And then this is an aqueous, so it's going to be, again, there's 2 potassiums there. So be careful, don't write K2, write 2K plus. Okay, so again, that's the ionic equation. Or if you want to call it total ionic or complete ionic, whatever you want to call it. I've seen it stated always. Okay. Now we write the net ionic. The net ionic is shorter. And this is really what we want to be able to write, the net ionic equation. You look at the solid. So here's your solid, MnOH2. And then you look at what ions made that up. It was the manganese and the hydroxide. So manganese. And then 2 hydroxides. And the net ionic equation should be balanced just like the ionic equation is too, and the equation you started off with. So this would be the net ionic. And what it says is, if you can get manganese ions and hydroxide ions in water at the same time, they will react with each other to form this precipitate. And what you would see, manganese actually has a color. What you would see is that you get these little crystals that would form. And those little crystals are the manganese hydroxide. Okay. It's insoluble in water. And then in the water would actually be electrically conductive because the potassium and the sulfate would be dissolved in there. You'd have K plus and you'd have SO4 2 minus. So those ions will remain dissolved in the water, and those are called spectator ions. The spectator ions are the ions that do not appear in the net ionic equation. They're the ones that are in the solution, but don't form the precipitate. Those are called spectator ions. Okay. Any questions on writing net ionic equations?
Really quick question. If you had a situation where you had, let's say 2 K2SO4 and you're breaking it up, would you get 4 K plus?
Yeah, you'd have 4, exactly.
Okay.
That's right. And then keep in mind the ionic compounds, they break up into ions. Molecular compounds don't. So like, if you took sugar, here's an example of sugar, C12H22O11. You might be tempted to say, oh, well, that's going to break up into ions. But if you have a hydrocarbon, they actually don't break up into ions. So if you dissolve it into water, we often write water underneath the arrow or above. Sometimes people write above. It dissolves. So it actually does become aqueous. And it appears to do exactly the same thing that table salt does. You watch it, you mix it, it sprinkles in and it dissolves, right? So you would think that it does exactly the same thing that salts do, but it doesn't. It actually just breaks up into individual molecules without charges. And you can show that that's true by sticking a wire and trying to pass an electrical current through it. If you put sugar in water, or if you put alcohols in water, they don't conduct electricity because they don't form any ions, whereas ionic compounds do. So physically, it's a very different process, the way that sugars and alcohols dissolve into water, we call them molecular substances, because they form molecules, they don't actually form ions in the solution. Okay. So there we go. Let's take a look.
Professor, this is the one that says net ionic. That's the final answer.
Yeah, that's the final. So the one that I put in a box, that's your final answer. Yeah, that's right. Okay, so let's take a look.
I'm sorry, Professor, if you don't mind this. The SO4, like, could you just explain why exactly did it disappear again?
Why it's what?
Why exactly is it not there in the last final equation?
Oh, why it's not in there?
Yeah.
Because you're only writing the ones that form the solid. So MnOH is your solid over here. So the net ionic equation is only going to include the things that make the solid. We're trying to analyze the formation of a solid. So if it isn't part of the solid, it's not important.
Okay, thank you.
So like when you buy medications are often salts. So medications often have chloride attached to them. So you got this big molecule. Okay, so here's your medication. And it turns out the chloride's unimportant. It doesn't have any pharmaceutical use. Your body just takes it in as an ion, but it doesn't really affect much in terms of your physiology. But you need that in there because you need a compound that you can make as a solid, right? So you have this solid. Then when it goes into your stomach, it's now aqueous. There's water around. So you want to have something that dissolves, right? So if it doesn't dissolve, it's not going to be active. So you put a chloride in. So, you could write it like ACl, right? So there's your solid. You put it into the water and you get your A plus and your Cl minus. And this is in there, but it's not pharmaceutically active. This one is, right? So same thing here, in order to get the manganese into the water so that we can react it with hydroxide to form this solid here, we had to have something that it could combine with that dissolves, and that would be the sulfate. So we're not particularly interested in the sulfate. We're just using the sulfate to get it into water. Okay. Can't have individual ions in nature. Individual ions, like just a manganese ion, is got a lot of energy and it would be very reactive. So we never have like, a container that just has ions, and it's got to be in the form of a compound.
Thank you.
Mhm. Okay, this one looks good. Okay, so the next thing we're going to do is we're going to use something called the solubility guidelines or solubility rules. They used to call them rules, now they call them guidelines. And it's in this third type of problem from the same section. So this is still section 4.2 called predicting precipitation. So now we're going to go to the next step in terms of making predictions about reactions. Okay, so the first thing to say about this is that you're going to want to open up in the ALEX or your textbook, the ebook, a table which shows you what types of compounds precipitate and which ones don't. And those are called the solubility guidelines, right? So what I'm going to do is I'm going to open up. Let's see if I can do it this way. Oops. There we go. Luckily, it did that correctly. So let me come over here. I'm gonna, oops, share screen. Oh, that's odd. Let's see if we can share this. Okay. Yeah, now you can see that a little bit. So I just typed into Google, I just typed in solubility guidelines, and then you'll see a bunch of images pop up. And, generally if I'm doing something online, like homework problems, I don't like to open up the stuff from the same program. So I'll just open up a different window. So you can do this, you can just do a little search for it. Okay, let me stop share. And then I'm going to bring up what they look like. Let me just go to images. And you can pick whichever one. I'm going to pick one that's actually kind of an older textbook. Problem is these days, what's happening is these websites are trying to steal these documents and then charge you money to use them, which is amazing. Okay, good. That should be pretty good. Let's see how this works. Okay, so hopefully you can see that. So it says table 4.1, solubility guidelines for common ionic compounds in water. These are essentially the same ones that are in your textbook, in your ebook. And what it said, what's generally set up as is two groups of rules. And the first group are the substances, the ionic compounds that dissolve into water. So it's telling you what dissolves into water. So for example, if a compound has the nitrate ion, NO3 minus, it dissolves. So you know it's going to be aqueous. So you won't see in these equations, something with NO3 in it that's solid, because nitrates always dissolve into water. And notice there's no exceptions to that. It says none in the right column. So KNO3 would be aqueous. NaNO3 would be aqueous. CaNO3 would be aqueous. Anything that has the NO3 is going to be aqueous. The second ion there is called acetate, C2H3O2 minus. And that one as well, there's no exceptions to it. This is often how chemists will get things to dissolve into water. So for example, if you have a metal you want to dissolve into water, you combine it with the nitrate and then store it. And then when you're ready to put that metal ion into water, you just throw it into the water. And because it has nitrate in it, it will dissolve. Chloride, Cl minus, Br minus, I minus, those are chloride, bromide, and iodide. Those are halides. They're from the halogen group 7A. They also dissolve in the water with almost every metal. But notice those three have some exceptions. The exceptions are if they're combined with silver, Ag+, mercury, Hg2, 2+. It's actually a peculiar form of mercury. It's called mercury 1, which is not the most common form of mercury. So it's kind of odd that textbooks keep putting in mercury 1 there because almost no one uses mercury 1. It's really in there just for textbook questions. And lead, Pb plus 2. Now that's significant because what that tells you is that if you add chloride to water, it will react with lead to form a precipitate. So when it says important exceptions, what that's telling you is that anion, chloride, for example, if you combine it with any of those metals, it will precipitate out. So this actually gives you a good way to get rid of some toxic metals. Lead is toxic, it's a neurotoxin. So if you add chloride to water, table salt, right? If you add salt to water, it will react with, the chloride will react with the lead and form a precipitate. Now you've taken the lead out of the water. Okay, so lead's actually pretty easy to get out of water as long as you know that it's in there, then you can take proper precautions to get rid of it. Mercury is also a neurotoxin. It's these days relatively rare, but mercury comes in the form of batteries. Alkaline batteries used to use mercury in high quantities. Now they don't, but older batteries did use mercury. Silver is not necessarily a neurotoxin, but it's a very valuable metal. So you might want to precipitate it out. So chloride, bromide, and iodide can precipitate it out. But the point of that, the main point, is that chloride, bromide, and iodide salts are generally very soluble in water. There's only 3 metals in the entire periodic table that we would write as exceptions to that. So if you added manganese with chloride, or magnesium with bromide, or gold with iodide, they should be soluble. They should dissolve into water pretty nicely. And then the last one is sulfates. Sulfates are generally very soluble as well. That's why they're in this first part. These are the compounds that are pretty soluble. But there are a couple exceptions there. So see what the exceptions are. There's strontium, barium, mercury 1, and lead 2. So those particular metals will form precipitates with sulfate. The sulfate is interesting in terms of barium. Barium is what's called a contrast agent. It will essentially absorb X-rays, but it's also toxic. Barium absorbs X-rays. It's a heavy metal. Heavy metals often will absorb X-rays, but it's also toxic. So that's an issue. So often it is the case we want to put things in the digestive tract to look for blockages. So if you have cancer or something like that, you might have a blockage in your digestive tract. So what you can do is you can take an emulsion of barium sulfate, because barium sulfate is the exception. Barium sulfate doesn't dissolve, right? So sulfates usually do, but not if they're with barium. So you take this emulsion, it kind of looks like milk. You drink it, it goes into your digestive tract, but because the barium sulfate is a solid, the barium sulfate will tend to get stuck if there's small blockages in the digestive tract. But also because it's with sulfate, the barium is no longer toxic because it's not in the form of Ba+2, it's in the form of BaSO4, so it doesn't have the same metabolic effects on your system. So it's non-toxic, just goes through your system, but more slowly if you have a blockage. Okay, so
That's the stuff that you're drinking when you're going for like a CT scan or whatever you're going for.
Yeah, that's for the CT. I think it's the
Yeah.
CT scan. Yeah, because CT scans use X-rays. That's right. Yeah, there's other contrast agents as well. There's fluorescent contrast agents as well, but the older and more crude one is the barium sulfate, which they still use. They still use that one. It looks like milk of magnesia. Okay. Now, really, if you think about it, we're not talking about very many species in this list, right? We just went over nitrate, acetate, chloride, bromide, iodide, and sulfates. So there's a lot of different compounds out there that we're just ignoring. We're not going over those. And if you wanted to know about those, you would look those up, or you might have to study them. It might be hard to find it in the literature because people haven't done it for a long time. But those are the most common ones. Now, the second group are the ones that are generally insoluble. These ones will precipitate out. They don't dissolve into water, right? So if you have sulfide, S2 minus, sulfides are famous for being insoluble. They don't dissolve in water very well. However, there's some exceptions to them. And the exception is if you've got ammonium, NH4 plus, the alkali metal cations. Now, they just kind of slip that in there without showing you what they are. The alkali metal ions are lithium, sodium, potassium, rubidium, and cesium. That first row, that first column, sorry, first column, column 1A. Okay, now anything that has that column A, if it's got sulfide, it will dissolve. So there are ways to get sulfide to dissolve. You have to combine it with either ammonium, the alkali metals, lithium through cesium, or calcium, strontium, and barium. That's actually a lot of exceptions if you think about it. It's a total of 10 exceptions or 9. But remember, there's a lot of metals in the periodic table. There's iron, there's cobalt, there's nickel, there's aluminum, there's gold, there's silver, there's lead, there's mercury, zinc. You could go on, right? If you look at the periodic table, which has in nature 92 elements, roughly speaking, around 70 to 75 are metals. So most of the periodic table is made up of metals. So out of all of those metals, the vast majority of them, if you combine them with sulfide, will precipitate out. So sulfide is pretty easy to get out of water. You can add almost any metal to it and it will precipitate. Carbonates are generally insoluble, but there are a few exceptions to that as well. So if you combine it with ammonium or again, the alkali metals, lithium, sodium, potassium, rubidium, cesium, group 1A, those ones are soluble. They will dissolve. So when you do these problems, if you see an alkali metal, it's going to be soluble. It's always soluble. But most carbonates are not. So that's why on the earth, many animals use calcium carbonate as a shell. It's a very good shell because calcium and carbonate are insoluble in water. Calcium is not one of the exceptions to carbonate. Calcium is also quite readily available. And then phosphate. Phosphates are generally insoluble. So calcium phosphate, for example, is a component of your bone. That's, it's part of the crystal structure of your bone. And most phosphates are insoluble. They don't dissolve very well. Again, the exception is the ammonium ion, NH4 plus the alkali metals. Hydroxide is generally insoluble, but there are more exceptions with hydroxide. So the hydroxide, the exceptions are, again, the alkali metals. They're always soluble. Ammonium, always soluble. And then you got your calcium, strontium, and barium. So be careful. I would print this out, have it available for you yourself so that you can refer to it. Because it's easy to get confused on this. Because if you take a look at it, the hydroxide rules are, the hydroxide rules look pretty much the same as sulfide, and they're almost the same as carbonate and phosphate, but not quite, the carbonate and phosphate don't have calcium, strontium, or barium in there. So be careful with those. But keep in mind the general picture. The first set of rules are soluble except, and then the second group are insoluble except. Okay, so let's take a look then at a problem. Let me hide that. Here we go. And this question is just going to ask you whether things form a precipitate, and if they do, what does it form? What's the chemical formula, the empirical formula of it? And here you go. Now, you'll have to practice, with your periodic table going from the name to the formula, right? Because you need to write the formula at the end. Okay. So let's take a look at this. So the first one, solution A, is zinc sulfate. And you're going to combine that with solution B, which is iron 2 bromide. So we're predicting whether things form a precipitate or not. So zinc sulfate and iron 2 bromide. Oops. So zinc sulfate and iron 2 bromide. Okay, so the first thing you want to do is you want to write the chemical formulas for this to see what's going on. Okay, so zinc is Zn. Now, we went over it earlier in the week that aluminum, which is element number 13, is +3. Zinc is element number 30, it's +2. And then silver is element number 47, is +1. So zinc is +2. Generally, you want to write the number and then the charge as an ion. Okay. And then you got your sulfate. Well, sulfate is SO4 2-. That's your sulfate ion. Okay. And remember, there was a rule about sulfate in there, right? We saw something, in the generally soluble that they were soluble with a few exceptions, right? So the issue here is, what happens. Okay. Now, what about the second one? So what I'm going to do just for this type of problem is I'm going to write the second one right underneath the first one. So I'm going to write the iron. Now, remember the Roman numeral system? If it has a Roman numeral, that's telling you the charge. So that's +2. So that's nice and easy. It's telling you the charge. And then you get bromide. Bromide is in group 7A. Group 7A is -1. Okay. Now, notice all I'm doing for this particular problem is I'm just writing down the formulas of the ions. I'm not worrying about how many, whether there's 2 of them, Iron 2 bromide would actually be FeBr2. So if the question was, what's the formula of iron 2 bromide, that would have to have 2 bromides. But all I'm doing here is I'm trying to figure out whether something precipitates. So all I need to do is figure out which ions are in there. And I wrote the second one right underneath the first one. And here's why. When you do a precipitation reaction, it's called a double replacement. The metal from the first one is going to combine with the non-metal for the second. So I'm drawing a little arrow. So, you got your metal for this one and your non-metal for that one. So a little arrow there. They're going to form a compound. Then you take the metal for the second one and you combine it with the non-metal of the first one. They're switching partners, right? So imagine you got 2 pairs and they just switch. They're just going to flip. Actually, you do it like this, right? Flip it over and then they break off. So essentially this one is, to draw a little arrow, this one's going to go with this one. And then the metal's going to go with this one. Okay. So now you're going to have 2 new compounds. Okay. The new compounds are going to be the iron with the sulfate. And now you got to get the formulas right. You got the zinc with the bromide. But bromide is only -1, zinc is 2, so you need 2 bromides. Got to balance that electrical charge. Okay. So those are your products. Now you go to the guidelines. You go to your solubility guidelines and you look to see if there's anything you can tell. The first thing I notice is you've got a sulfate. And we had a rule about sulfates. Sulfates were generally soluble, but they had some exceptions, right? So let me just do this. Let me save this to photos. Oops. Okay, so let me, because I don't want to lose that. Here. Oh, shoot. Okay. Sorry, hold on 1 second. Bring it back. I want you to see it. Okay. Now I can share this. There you go. Okay, so I'm sorry. So there's your sulfate. So sulfate is the last one in the soluble group. And what it says is sulfates are soluble unless they're with strontium, barium, mercury 1, or lead 2. Okay. Well, we don't have any of those metals in this particular problem, right? So that means we don't have to worry about the exception. So that tells us the sulfate is going to be soluble. Okay. Now, there's also noticing in here, there's something about bromide. See how there's a bromide there? Bromide is generally soluble unless it's with silver, mercury 1, or lead 2. Okay, so now we can kind of look at both of them. Let me stop sharing here. Here. Oops. Shoot. Okay. So let's come over here. Sorry. Okay. So make sure I'm sharing the right thing. Okay, good. So these are two comments. So what we found was that, you know, iron is not one of the exceptions. So sulfate with iron should be soluble. And bromide is generally soluble unless it's with one of those three metals. Zinc is not one of those three metals, so it's also soluble. Okay, so both of our products are soluble. So then when we come back to the question, okay, zinc sulfate plus iron bromide, the answer is no. There really isn't any precipitate that's going to form because both of the compounds that we formed out of this are soluble in water. So no, there isn't. And if there isn't a precipitate, then there's no empirical formula. There's no formula for the precipitate because none of them actually were formed. So this would be an example where you added two salts into water and they just dissolved in the water and didn't do anything. They didn't form any solids there. They would just remain, they're all spectator ions in a sense. Okay. Let's take a look at the second one. So that one was kind of boring. Nothing happened, no reaction. Second one is potassium hydroxide and iron 3 sulfate. So this one's going to be a little trickier in terms of the formula, but not so much so. So potassium hydroxide and iron 3 sulfate. Let's take a look at that one. So potassium hydroxide and iron 3 sulfate. So another sulfate. Okay, so potassium. Potassium is K. It's in group 1A, so it's K plus. Hydroxide, polyatomic ion, OH minus. Okay. The second reactant, iron 3. So that's Fe for iron. And then its charge is +3. And then you got your sulfate again. So we have another sulfate, SO4 2 minus. Okay. Remember, you switch partners, right? So now the potassium is going to go with the sulfate. So this will go with the sulfate. And then the iron is going to go with the hydroxide. So iron is going to go with hydroxide. When you're writing chemical formulas, you do want to write the metal first in general. There are some exceptions to that, but generally you want to write in the formula the metal, then the non-metal. Okay. Strictly speaking, you're writing the cation and then the anion. So K, now K is only +1, sulfate is -2. So it's really K2SO4, right? Because you need two of the positives to balance the -2. And then same thing here, you've got hydroxide is only -1, iron's +3, so you need 3 hydroxides. So Fe, if you've got a polyatomic ion, you want to write the parentheses in there. So 3 hydroxides.
Why are we doing K2 again, not K3?
Oh, because you're doing K2 because you're trying to balance the charge. This one's -2.
Oh, it's not -3, even though it says iron 3 sulfate.
Iron 3 means Fe+3, so that's right there.
Okay, it
So
doesn't
the
say
hydroxide, there's
anything
3
about.
hydroxides. You're right. There's 3 hydroxides because the iron is +3.
Does the Roman numeral after iron say anything about the sulfate? Like, do you have SO4 3?
No, the Roman numeral refers to the metal.
Okay.
It's telling you the charge.
Oh, got it. Okay.
Technically, it's giving you what's called the oxidation number, the oxidation state, but
Mhm.
for all practical purposes, it's the same as the charge.
So
it's telling you
if you were doing like the chemical formula for iron 3 sulfate, would it be just Fe3SO4?
So here's what you do. You'd say, hey, iron is 3, right? That's the charge, 3. Sulfate is -2. Can't change that. So now you have to say, well, how are they going to combine so that their charges are equal, right? So what you do is you say, look, each one of these is +3. So what if I had 2 of them? That would give you a total of +6, right? Each one's +3. So then you'd need 3 of these. That would give you -6. So it looks like the way they're going to combine is 2 of these and 3 of these. So the way you would write that would be you write the metal, 2 of them, that means 2 irons. And then you write the non-metal, 3 of those, that means 3 of them. Okay. Sometimes what people will do is they'll just switch the numbers. They'll say, hey, if this is a 3 and a 2, then you're going to have 3 of these and 2 of those. So you get Fe2SO4. You got to put a parentheses in there, SO43. So sometimes people do that. You have to be careful doing that method, though, because you just have to remember, like if you have Fe2 plus and O2 minus, you don't switch the numbers here. That would give you Fe2O2, which you could do, but ionic compounds are always written as empirical formulas. And so the empirical formula of this would be FeO. So there we go. Okay, so we got our 2 compounds, K2SO4. Let's do the first one. This one actually has sulfate in it. And the general rule for sulfate was it's always soluble unless it's combined with, what was it? Was it mercury, lead, barium, and calcium? I think those, and strontium. Those were the 5. Potassium is not one of those 5. So that means it's aqueous because of the rule about sulfate. And then the last one, the iron hydroxide, hydroxides were generally insoluble unless they were with ammonium, alkali metals, barium, calcium, strontium, right? So iron is not one of those metals. So being in the second group, the general rule is insoluble. So this one is a soluble. I mean, it is a solid. So this one's a precipitate. Right? So that one will precipitate. This one's aqueous. Right? So these are spectator ions, just to bring it back to the previous question. Right? The ones that don't form the precipitate are called spectator ions. So potassium and sulfate are spectator ions. So it doesn't actually form a compound. And that's kind of the important point of this. Even though we're writing it as a chemical formula, it's not really going to form a compound. It's going to be dissolved into the water. It's going to be in the form of ions. But if it forms a solid, then it is an actual compound that forms. So that's why, like in terms of kidney stones, they recommend that you be careful in terms of your oxalate intake, because oxalate can form these calcium crystals, which can cause a lot of pain. So how do you do that? Well, part of it's genetic, but the other part is that you have to limit how much coffee you drink and how much tea you drink and how much chocolate you eat and how much wine you drink, because those are all substances that have a lot of oxalate. Generally, it's not the case that people recommend you cut down the amount of calcium in your diet. So that's kind of tricky. You probably don't want to cut down the amount of calcium. So you got to limit the amount of oxalate that's in there. But there are also kidney stones that are formed out of phosphates. So magnesium phosphate and calcium phosphate. Again, you don't generally want to cut down your magnesium and calcium content in your diet, but you might want to be careful with phosphates, and phosphates are often in fish, right? So it's tricky. Part of it's genetic, just depends on how lucky you are. But generally, drinking lots of water helps, dissolves these crystals a little bit. Okay, so let's do the third one. So in the first one, but our formula is right here. So if we want the empirical formula, we have that right there, FeOH3. So that's the empirical formula of the precipitate. So the first one, no precipitate. Second one, we got a precipitate. Third one, I would predict you're probably going to get a precipitate for the third one. It'd be strange to have two where you didn't get a precipitate, but we'll see. Let's take a look at the third one. Okay, third one, predicting precipitation. Complete the table below. Okay, so here we have potassium hydroxide and ammonium bromide. Okay, well, actually, ammonium, what we found when we looked at those exceptions, ammonium is generally pretty soluble. So that's kind of interesting. And potassium is as well. Those alkali metals are generally pretty soluble. So we may not actually get a precipitate out of this third one. Let's take a look at it. Potassium hydroxide, so that's KOH and ammonium bromide. Okay. So potassium hydroxide. We're going to talk more about potassium hydroxide when we get to acids and bases. And ammonium bromide. Okay. If you've forgotten the polyatomic ions, there's a list of them in your second chapter of your textbook. When you get into, it's in chapter 2, very late in the chapter, because it's all about naming compounds. There's, all the important polyatomic ions are listed there. Actually, the important monatomic ions are there too, but if you forgot them. So potassium, group 1A, K+. Remember, the first column of elements, group 1A, we call them, they're +1. Second group, group 2A, those are +2. So there's that one. Hydroxide's a polyatomic ion with a charge of -1. So that'll be in that list of polyatomic ions. Ammonium is in that list of polyatomic ions, but it's also in the solubility. Actually, that list of solubility guidelines is kind of useful because it also lists a lot of the polyatomic ions. It gives you the formulas in there. In any case, ammonium is NH4+. And then bromide is group 7A. Group 7A is -1, but you can also find it in the solubility guidelines, Br-. Okay. Okay, so let's bring it down like I did with the previous two. I'm going to bring these down here. And then switch partners. So the potassium is going to go with the bromide. The nice thing about this one is everything's +1 and -1. So you don't have to have two of these and 3 of those. It's all very nice. Okay. So there we go. So let's do the first one, KBr. They're going to combine 1 to 1 because they're both have a charge of 1. And then so does the ammonium hydroxide, NH4. Now this is an interesting compound, right? There's no metal in that one. Ammonium is not a metal. It's, nitrogen's not a metal, hydrogen's not a metal, oxygen's not a. So this is an example of an ionic compound without metals. Doesn't actually have any metals. So ammonium is a very interesting substance. It's biologically important, probably important in terms of the evolution of life on the earth altogether. Okay. This is an interesting thing. It actually kind of acts like a metal in a sense. It's like a little particle. It's a polyatomic ion. It acts like a little positive charge, just like a metal, but it will combine with nonmetals as well. Okay. So we look through our solubility guidelines. Bromide, there's one in the top part. Bromide is generally soluble unless it's with silver, mercury 1, or lead. Potassium is not one of those metals, so it's aqueous. Okay. Ammonium hydroxide. Hydroxides are generally insoluble unless they're with ammonium group 1 metals and then a couple of the group 2 metals. So this is actually one of the exceptions. So it's soluble because of the ammonium. All right, so that one's aqueous. So the third one, actually, so I was wrong. The third one, we actually have no precipitate here. PPT for precipitate. No precipitate here. PPT. So in fact, this example, no precipitate. So no need to write an empirical formula of a precipitate because there isn't any precipitate there. Okay. And there you go. So that's our discussion of precipitation reactions, which are, strictly speaking, probably the most boring of the chemical reactions, but they can be kind of fun to look at. And certainly life forms depend on them. Our bones are essentially formed from precipitation reactions. So that's kind of important, right? And over time, as we age, the proteins, our collagen in our bones actually gets replaced by calcium phosphate. And so over time, our bones become more crystallized in the form of a precipitation reaction. So it does have applications in terms of our health. But what we're going to move on to next, which will be next week, is acid-base reactions. Unfortunately, in this course, we don't really go into great details about acid-base reactions. We just kind of look at them from a pretty simplistic perspective. And then we'll look at some of the more energetic reactions, which are called reduction oxidation reactions or oxidation reduction reactions. So we'll look at redox reactions as well coming up next week. And then we'll look at what's called concentrations of solutions, molarity. We'll look at molarity calculations as well. So that's all coming up next week. Any questions? All right. Very good. So have a great day. Have a great weekend. And I think there's some deadlines coming up this Sunday, so pay attention to your deadlines in the syllabus and all of that. Try to keep up on that, and we'll see you next week. Take care.
Thank you. Have a good weekend.
Thank you. Bye-bye.
Bye.